Day. I signed up for the class yesterday, and I haven't figured out how to do my cloning of the project yet. But
Okay.
if I run into any issues, I'll let you know.
Okay, not a problem. I'm actually going to go back over it again this morning anyways, so that's
I
not
appreciate
a
it. Thanks.
problem. Okay, so I'm going to start by saying welcome back everybody to PCB Design Fundamentals Part 2. This is our second week. This is where we're going to actually start getting significantly into the project work. For those coming back from PCB 1, um, the Altium should be pretty familiar to you. So we'll go ahead and we'll jump in here. So the very first thing we're going to do after we open Altium, again, for the new gentleman who just joined us, let's make sure first that that you have your Altium license. And I apologize, I missed your name, new gentleman who just signed up yesterday. I did not see that pop up there. So why don't we start with that? Last week we went around and introduced yourself. So new person who signed up, go ahead, open your mic, introduce yourself. Just tell us your name, where you're located at, and what brought you, what interests you in coming to a PCB design class.
Yeah, of course. Can you hear me all right?
Yep, we can hear you just fine.
Yeah, so my name is Vaibhav, but I go by Vibes. I currently work at Amazon Prime Air, and I'm a hardware development engineer who recently, less than 2 years ago, graduated from university. So I have experience with Altium, and I just really wanted to focus on my layout and getting more involved with thinking about manufacturability and design cycle and reliability. So I just thought this class would be great to go over the IPC certification as well, thinking about design.
Excellent. Welcome, Vibe. So are you up in the Seattle area at Amazon's
I
headquarters?
am.
Cool. I
Yeah,
spent a
I
year
am.
up there. Yeah. I spent a year up there working for Blue Origin before I joined IPC directly. So very
Oh,
nice
that's
area.
cool. Yeah, I heard you were working at Blue Origin in your intro video, and I thought it would be pretty cool.
Yep. Yep. Got to work on New Shepard, actually. I got to work on the module that took Captain Kirk to space for real. So
Nice.
that was fun. Okay. So Vibe, so one of the things we're going to need, so do you already have an existing Altium license you can use, either through university or your own personal one or through work, or do you need the
Yeah.
license? Okay, you do have that. Okay, so the
Yeah,
first
I
thing,
think I'm using Altium 19 or 21. I'll have to double check.
yep, it's okay as long as you're using one of the newer ones. Um, the first thing you need to do then is just send an email. And Kelly, could you drop into the chat the education2 and my email address so Vibe grabs them real quick?
Sure.
Kelly's going to drop into the chat window. We have an education email address as well as my personal IPC email address. If you could email us or send us what email it is you actually use to log into Altium so that we can add you to our workspace. Vibe.
Sounds good.
Okay, and yeah, don't drop your email in the chat. Just send it to us because we'll do it after. I might be able
All
to get
right.
to it at break. But once you are added into the Altium 365 workspace, I should ask you this, Vibe. Through Amazon Air, do you guys use the Altium 365 workspace, cloud-based file storage, or do you maintain everything on your own internal servers?
I think we have some sort of a hybrid right now. So most of the parts and component libraries are internal, but some of the files are stored online on Altium 365.
Okay, so you are familiar with the Altium 365 then. Okay.
Yeah.
So what's going to happen is you're going to get an invite to the IPC Altium 365 invite. So up here under your normal cloud access area up here, and just a refresher for everybody that I showed last week, you'll simply click the little cloud icon up here, and you'll see the IPC Education Workspace account. And by the way, Kelly and I did rename it this week. So basically, for those that saw last week where it's an IPC corporate account, not for students, blah, blah, we just renamed it because we commandeered it for education. So it's now called the IPC Education Workspace account. It's the exact same place you were at. So once you get access to that, you'll see it here under your list of available workspaces. You'll simply connect to that workspace right there. That'll be the one you're connected to. And the first thing you're going to do when you go up in there for the cloning process is you will pick that workspace. Sorry, pull the little pull down again. And in this little web or globe icon right here, click the little globe icon, which will open up the web interface to that icon there. And there'll be a bunch of, welcome to 365, getting started, some videos there if you want them, and so on. But the main area you're going to go to is this projects folder area right here. And in the projects folder, I have gone ahead and created a number of subfolders based off of the various different courses, so I've got it by class and quarter. So here we are, here's, PCB2 quarter 4 of 23. So this is where we're going to work at. I then also have in the root there a bunch of starting point projects or templates to start from. So we'll find this one here, the IPC, where did I put it? Project 2, project course 2 start point right here, the PCB2 start point project right here, Vibe. You'll simply click the 3 little dots and you will choose the clone option right here. Now, the first thing I want everybody to do is to rename the project by the name of the class. For this course, specifically for PCB 1 and 2, you only need to call it the PCB 1 or PCB 2 course. It's the same project over the duration of the course. With my other courses like Mill Aero, RF, and other ones, I have new projects every week. So I also want you to put the week in like RF week 2 project, RF week 3 project, and so on. But for this one, we can just call it the name of the actual course, which is PCB2. Underbar, the quarter. So in this case, like Q4-23, you can call it Q4 underbar 23, Q4 underbar 2023, just so I know quarter and year. And then finally, underbar and your name. Again, this helps me, so when I'm providing feedback, I don't have 20 copies of a project all called PCB2 quarter 4 of 23, right? It's one thing, it's the same thing that happens when I teach at university. The students all think that on their computer, they have a single file called project 2 report. And then I, as the instructor, get 20 copies of a file called project 2 report. It's the same thing. So to help me figure out whose project is whose when I'm looking through to give feedback, please change the naming convention like you see it right here. Okay, and then you also click the advanced button right here. And for the parent folder right here, instead of the root projects folder, click the change button right here. Expand the projects group and find PCB2 of Q4 of 23. Select that as the folder and hit clone. Okay. Oh, and I've already demoed this last week, so my copy of it already exists in there. I have another copy I just created this morning where I called it K Moyer, but instead what I'll do is I will change this from Chris Moyer. I will change this back here to just be K dash Moyer, whatever, just so it's got a unique name. And then when I hit the clone, it will give it a unique name right here. And once it's done, and that project is, so there's K dash Moyer, there's Chris underbar Moyer, K Moyer that just created. There's a bunch of copies of it in here because again, I demo this multiple times. You can then minimize the web interface and simply go over here. As you're logged in, you will then see in your projects tab, you'll see your local project workspace here and your web-based or A365 cloud-based workspace here. You can click either the 3 dots right here or the normal file right here, open project. Either one will take you to the exact same place. It'll take you to the open project dialog right here. And what you'll do is if you're currently pointed at your local projects, just to make sure that you change it to your cloud-based projects here. And mine, because I have so many projects I have available to me, and my computer's getting old and slow and will be replaced over the holiday break. What we have right here is the, here's the cloud-based, and we can see by when it was created and so on. So there's the new one, K-Moyer I just created. So you'll find yours, and you just click the standard open button right here. and it's using Git the Git technology for GitHubs, like for software development. So it's going to extract or check out a copy of the project. It will clone it to your local area of your hard drive. The default location is the C drive in like the users area where users, project data, project files, and stuff like that goes. Normally that Windows defines. You can change that if you're interested. I can show you the configuration how to change that. But in just a moment here, you'll see the new instance project show up at the bottom of my project list. There it is right here. And from there, now it is exactly the same behavior as you're used to with a local version project, where you have, the organizational folders underneath, source documents, settings folders, libraries, other documents, and so on right here. The difference is now you're going to have the save to server option right here, as well as the server status icon, in addition to the document status icon. So Vibe, you should be familiar with Altium, that when you modify a document, the little document here turns red, saying you've modified it but haven't saved it yet. You are now also going to get these green checks or red circles and a few other, like a yellow little silhouette icon and stuff that shows when other people are working on it for collaboration and so on. But effectively, you will get this view right here, and then you can do the same thing, just open documents and so on. So I now have all of the project documents open. There's a couple extra that I opened that I didn't need to at this time, such as my draftsman documents, we'll see towards the end of the course. So I'm going to close the draftsman document. So we're looking at just schematics and PCB document. Are you good with that now, Vibe, on how the cloning is going to work, as well as other folks out there? Okay, Vibe, you're good?
Yeah, thank you.
Yeah, not a problem. Okay, for other folks out there, is everybody else out there good with how the tool is going to work from a point of view of adding in the opening the project from the 365 server? Okay, now the other thing here in the PCB document, we did a brief look last week at the PCB document, but I do want to show you guys something here. There's a red X. So red X was Mattia. Mattia, you've got a red X and a thumbs up. I'm confused. Does that mean you are or are not good with
No, I'm good. I'm confused with Zoom.
Confused with Zoom.
Yeah,
Alrighty
sorry
then.
about that.
No worries. I'll just clear that for you. I'll make your red X go away. Okay. There is another feature in Altium I'll show you. So the template I provided in course 1, as well as in course 2, it's also up there on the server. So once you're in our 365 workspace, I do provide my default template project I've created over 30 years. I give it away now for free to everyone. So that everyone has a good starting point for projects. It's based off of my university I teach at, so Sac State University right here, CSUS. For those that are not familiar, so prior to the development of the draftsman tool in Altium, we used to have to do all of our documentation directly within the PCB document itself. I have all of that shown in here still as just a nice to have starting point. But what we can do actually to save size of our file and to keep all this stuff out of the way, this is a feature I've not demonstrated typically before. For those that know how to use it, fine. If not, I'll demonstrate here. In the selection, so under the Edit Select submenu, I can go say Select outside of the area and draw a box just around my board feature items right here. Let it select all of that stuff there and just delete, throw away all of that older stuff that was out there. And now when we go to do, we'll get rid of that one as well, delete that one as well. So now what we can do is we can go back to our schematic document. And again, if you're using my start point right here, we'll simply go and do the import. But before we go there, I am going to go back over here to our Edge page. Let me sign back into Edge. I signed out last night. So we're down here in week 2, and we'll go look at the week 2 assignment right here. And if we basically say, if you are starting with your project from course 1 and you did not complete the defining the net classes, go ahead and define the net classes now. Change the net class name PWR on the PWR page to 50 volts. Add differential parameter sets to thermistors on the thermistor page, and then update the PCB document. Also, we want to go, and now we're going to build our first Stackup modification. We talked a little bit about Stackups last week, as well as earlier on Monday of this week. We want to define a single-ended 50 ohm impedance and a differential 100 ohm impedance. For the DRC rules, we will define our DRC rules. For clearances, we will use the following. We'll use the B1 column for internal conductors and A7 for external conductors. And then we'll define clearance rules, right? So we're going to use the B1, the A7, and we want the following clearance rules. We want 50 volt, digital, and then we want width rules for 1 amp, 5 amp, and 10 amp. The width rule for digital based off of the single-ended 50 ohm, and the width rule for differential pairs for differential 100. Then we'll start pre-routing all of our repeated rooms and place all of our rooms and parts in the board according to the recommended parts location, which I'll show you here in a minute. So the first thing we're going to do, before we do any update, we'll do these first 3 steps right here in the schematic if they are not already done. So again, most of this is for folks coming back from PCB 1 who may be starting with your project that may have been in differing states. If you're starting with my start point project, the majority of that work is already done. And if you expand the hierarchy here, so let's go down here and look at the power page first. The power page, I believe I do have incorrect here. I left that incorrect so we could see how to do that. So we have our blanket right here. And down here in our blanket, we have this net class right here that I had called PWR. We're simply going to select that net class and change its name, its net class name, to the new name we want, which is simple 50 volt. Okay. So we'll change that there, and these are 10 amp nets for our power. Now, 10 amp, I will make the same statement I make at the beginning of all of my classes. I have done absolutely zero electrical engineering analysis on my design. Topologically, right, looking at the topologies of op-amp structures and linear regulator structures and so on, all of that is correct. But as far as component values, right, the fact that I'm saying this is a 10 amp net class, but if you actually pull the data sheets on any of these regulators I've used, they're like 1 amp rated parts and so on, so they would never be a 10 amp rated net. I'm doing this specifically from a teaching point of view to teach these methodologies and mechanics of routing and tools and placement and etc. So please take my design with a grain of salt and understand that I have intentionally done things in the design from a teaching point of view without actually doing the proper thorough electrical engineering analysis on this design. So we'll change that there first. Then we're going to go down here to our thermistor page, as we said right here. And on the 2 inputs right here, thermistor in, P and N, these are going to be a differential pair. So we're going to select those. I'm just going to move these over a little bit so I've got a little bit of room here. And what we're going to do is under the place menu, a directive, and we're going to do a differential pair directive right here. As with everything in Altium, whenever I'm in an action mode where I have something on my cursor and my cursor turns into the crosshair instead of just the arrow, I can hit the tab key, which will pause my action, bring up the properties panel, and allow me to make edits or modifications here. So the label itself is diff pair. I don't want to modify that. Instead, what I want to add is I want to click the little pull down here for add, and I want to add a diff pair net class. And for that name right here, I'm just going to call it generic name like diff pairs, right? This is the name of the net class, the name of the group of nets, right? This is not the name of the individual net. So I'm going to add this net here, as well as its partner net right there, to the group called diff pairs. I'm also, even though I don't have it in the rules, in the requirement, I'm also going to look at my pressure transducer, because my pressure transducer is also a differential pair, so I will make the same change over here. I'm only going to ask you guys to do it for the thermistors, but if you'd like to also come back here and do it for the pressure transducers, that is fine. And again, scroll down right here. Add. Come on, why is the mouse not registering there? My poor computer is old and slow now. It will be replaced over Christmas break. There we go, diff pair net class. There we go. Diff pairs. And I'm going to add those to those two nets as well. Everything else in here should already have their net classes defined. So in mine, I've got 50 volts, 1 amp, on memory, I've defined those as digital groups. So I've basically, in the schematic, I have pre-grouped my nets according to their functions and according to their ratings. Now, one of the things, and we talked about this a little bit this week and last week when I talked about the voltage clearances, that table 6-1 in IPC 2221. And I mentioned it in passing, and I'm going to go into it in a little bit more depth here. You'll notice that in all of my analog pages, for example, my potentiometer here, or the power supply, or whatever I was on, I rated everything at 50 volts right here, right? We're all good with that, the fact that I rated everything at 50 volts? Yes?
Yeah.
Now, we'll notice, however, that, well, this is not a good example. Let me look at the pressure transducer I was just in. Pressure transducer here, it's plus 15 volts for its power supply. My thermistor is plus and minus 15 volts, right? So I'm nowhere near my 50 volt rating. Okay. You know, here my op amp for my thermistor is a plus and minus 15 volt, right? And so on and so forth. So I have it all low, much lower voltages, but I have it all rated as 50 volts. And the question is why? Right? Why do I have it rated that way? And we'll go back and we're going to have a preview discussion on what we are going to get into in more detail when it comes to the manufacturing side of things. Okay. So over here in our IPC 2221 standard in section 6 for the electrical properties right here, we're going to get down here to the chart. We already looked at this chart before, but let's just look at it again. So 0 to 15 volts. This says for B1, I only need 2 mils, like 0.002 inch, right? 0.05 millimeter. Okay, the A7, the external is 5 mils, but that's still relatively small. I basically have these same very small numbers all the way up to 30 volt, or here, and up to 50 volts. I'm at 4 mils internal and still at the same 5 mils external. This is what IPC has empirically defined from an electrical point of view. based solely on voltage, how much gap do I need feature to feature based off of the voltage, right? So I don't have an arc overbend happen. However, and we will see this more when we get to manufacturing week, let me go over here. Whoop, sorry, that's isola for the laminates. I also want to go over here. Yeah, so right there, okay. What the heck? There we go. God, what is... Oh, that's like some kind of search history. Okay. If you look at the various different fabricators out there, and we're going to talk about this more when we get to manufacturing, but depending on the copper weight that you're going to pick for your layer, your fabricators are going to have much, much larger minimum feature spacings and feature sizes compared to what the electrical requirement is. So for example, on inner layers, assuming 1 ounce copper, the fabricator says the smallest they could do is 5 mil traces and 5 mil spaces right here. So regardless of the fact that I only have, digital voltage levels or, 12 or 15 volt power levels for my, analog power supplies, doesn't really matter because the fabricator is going to dictate to you what your minimum feature size and spacing is going to be from a manufacturability point of view. So to Vibe's question earlier about wanting to learn design for manufacturability, this is one of the key areas where many an engineer makes a mistake is they don't understand the manufacturing capabilities. And the IPC chart says you can do 2 mil clearances. So they route their whole board in 2 mil clearances and ask the fabricator to etch it in 1 ounce copper. And the fabricator says, can't do that. So the reason, just from my own personal 30 plus years of doing this, I've learned that unless I'm doing thinner than 1 ounce copper, pretty much 5 mil trace, 5 mil space is the smallest I'm ever going to do. So I'm just going to rate all of my voltage. I use that 50 volt rating as my intrinsically safe. You're also going to find that from an electrical engineering point of view. Most safety systems, 48 volts or 50 volts, about that is considered the intrinsically safe with little to no shock hazard. Where voltages over that are considered, now you need high voltage warnings and safety checks and so on your design. So I basically, in my designs, I will go ahead and use this 50 volt net class as my generic 50 volts and less for all of my analog ratings, unless I need over that rating. Right. So I'm sorry, I went off on a little side tangent there, but I wanted to explain why I used 50 volts here. And the same thing is going to end up holding true here for the 1 amp rating. Again, I will give you a little preview of manufacturability here, but I'm going to pull up a little tool that I use right here. We can also use the Saturn PCB, but I like this particular tool from UltraCAD better. And I'm going to say 1 ounce copper external, and I'm going to say 1 amp at 10 degrees C rise is like a 10 mil trace, right? So, or I should say a 5 mil trace, and we'll look at the internal at 10 degrees C rise. 5 mil trace, 1 ounce copper, internal, 10 degrees C rise. Yeah, that's like 0.75 of an amp, right? So my 5 mil trace is roughly, right? And if I say I want 1 amp, I'm going to get a 20 degree C rise. So I'm right there within my sweet spot of where temperature rises should be. So my 1 amp works out to be pretty much my minimum trace size. If I need anything over 1 amp, I'm going to redesign for something larger trace widths. But my 5 mil trace that I'm going to create here in my board is basically going to be good for my 1 amp of current on all of my layers. And we'll get more into that when we get into manufacturing weeks and so on. But so I basically use 50 volts and 1 amp in my net class definitions here as my intrinsically safe values. And again, more on that as we do our designs here shortly, right? So basically that tool I just showed you, Multiget, it's free now, by the way. I put a link to it on our Edge page to UltraCAD. His tools are all free now, free to anybody. And those tools will basically, his tool, he has a white paper for it that shows that he nearly exactly matches the current charts from IPC 2152 and so on. Okay, so doing that, so I have now created my differential pair net classes. I have modified the power class. So going back here and looking at our Edge page, so I've done that one, I've done that one. Now we need to update the document. And I should actually realize I should have made one other assumption here. Let me edit the settings right here. And I should do this. Assume 1 ounce copper for layers. So need to put those two assumption statements in there. Okay, so assuming 1 ounce copper for all layers and assuming class 3 plating for all plated through holes and the external layers. So that basically means our external copper layers after all the processing, and we'll see this in manufacturing, will actually end up being 2 ounce copper equivalent. And we're going to do our 1 ounce copper. So we're ready to go update our PCB document and then start making our design rules here. Okay. So first thing I'm going to do is with my schematic pages here, first I'm just going to save the two I just modified. Don't have to do this, but it's a habit I like to get into. Let me save that one. And save that one. Now you'll notice to Vibe and others who will be new to 365, I was talking about the server status. You'll notice that once I saved this one, the local document is now turned white, saying it's no longer modified, it's current, but the status of what is on the server is now out of date to what the local copy is. So I get the red circle right there. And that's fine. That's just telling me status, you know. It's checked out and modified and has not yet been saved to the server. And finally, I'll save my thermistor one that we did down here. And by the way, Vibe, since you're new, what I mentioned to the class last time, my class is very much a interactive, like a college class or university class would be. If you have any questions as we're going along, please don't hesitate to open your mic and ask, raise your hand, or put it in the chat. This is not intended to be a webinar where I lecture for, for 2 hours straight, and then you save all questions till the end. So just reiterating that for everybody out there. Additionally, when it comes to the Altium tool itself, if anybody has any tool questions that might not be specifically on what we're working on at the moment, please also don't hesitate to ask. I am pretty much a guru with this tool. I've been using it since it was created. So I pretty much know it inside and out. So if you do have any questions or would like any insights, again, please don't hesitate to ask. Okay, so we've saved our local copies right here. So now what we're going to do is we're going to use our simple design and say update the PCB document right here. And it's going to think for a second, and then it'll pop back up here with a little dialog box. Honestly, I promise the dialog box is going to pop up. While we're waiting at dialog box to pop up, does anybody have any questions out there? Okay, never mind. Dialog box popped up. One of the things, when this dialog box pops up, it comes with anything like match net names or anything of that nature, please just hit the continue. At this time, do not try to do the net name matching or anything like that. Just let it overwrite everything. So just hit the continue here. And then this, like net classes or anything like that, just continue through until you get the overall ECO box, which will pop up here. So this is going to tell you everything it's going to do, right? So it's showing you all of the pins, names, rooms, everything else that it's going to create. And I'm simply going to hit execute the changes right here. Let me go through. And you'll see the blue bar. It's going to, the first time when you've got a relatively large design, the first time through, it's going to give you it's going to take a little bit of time. And in fact, while that is completing, I will actually, no, it's almost done. Okay, it has completed. One sanity check I like to do is you should get 2 green checks, one for the check, one for the completed or the done column here. I like to take my scroll bar and just do, oh, it's still doing the blue bar. Never mind. While it's still doing the blue bar, I will go back here. And in here, in the week 2 area, remember I mentioned a place parts according to the document. This is a rough suggestion document. This is not a you must do this exactly document. So I have this main layout locations PDF right here. And this is going to be just, again, take this as a rough concept level where things should be. LCD at the top center, LED displays in a 4x4 array, power supplies somewhere over here on the right, digital stuff with the FPGA and the memory somewhere here top center, pressure transducers over here, thermistors here, Hall effects here, motor drivers here, switches roughly here, buttons roughly here. And again, does not have to follow this precisely. We're going to look at several slightly different techniques here, but this is just a concept of where things should be. So I do have this PDF document for you right here. You can open it up and download it and go from there. Okay, so I'm going to go back into the assignment here so we can continue looking at this assignment. Okay, now that the blue bar has completed here, the last thing I like to do before I hit the close right here is I like to scroll my little scroll bar up, and I'm looking to see if any red X's jump out at me. There shouldn't be, but if there are, that tells me there was some kind of an error that I need to go investigate. So nope, all green checks as I scroll through that. I'm going to hit the close, and what you're going to see now is you're going to see all of the various parts are brought in. You see all of the rubber bands over here. And for those that are new to PCB2 and possibly new to Altium, I did this design using what Altium calls their hierarchical structure, where I did repeated rooms. I have in the schematic, I have this page here called top. We go and look over here. And what I'm able to do is for where I need multiple copies of the same circuit, such as the pressure transducer, the thermistor, the Hall effects, and so on, rather than actually drawing the same circuit over and over and over again, I can simply draw the schematic page once and then come in here and using the repeat command on the page symbol right here, I can say make me 4 exact copies of that page. And we'll see why here in just a moment, why this is a super powerful feature. But the first thing we need to do is go and create our rules. Okay, so now we have everything brought into our PCB document right here. And before we do anything else, there's two things we need to do. Number one, we need to modify the stackup. Number two, we need to modify and create modify the stackup to include the differential pairs and the controlled impedances. And then also we need to create our rules. So first thing I'm going to do is over here under the design menu, I'm going to choose my layer stack manager. And again, my poor system is old and slow, and it's taking its sweet time to think here. So here's my default layer stackup that I have defined in here, okay? The first thing I'm going to do is I'm going to modify all this. You'll notice I've got 2-ounce copper for these two inner layers, layers 4 and 5. And I had show 2-ounce on the outer layer here, but this is the older style. So with the newer style in Altium, what I'm going to do is I'm going to go through each of these layers and select the little 3 dots right here. And I'm going to say I want this to be 1-ounce copper. Sorry, 2-ounce copper for the outer layers, my bad. And we're also going to make sure by default it should be enabled, this checkbox right here that says stack symmetry in the properties panel. Let me go back into that one. I want 2-ounce on the outer layer because we just said we're going to assume it's 1-ounce foil for the layer, but then we have 1 ounce of plating. So we're going to end up with 2 ounces total copper on the outer layers. And then for all of these inner layers right here, I'm going to choose the 1 ounce. And I'm going to choose my 1 ounce right here. And finally, I'm going to choose my 1 ounce right here. Well, we're doing this even though some of the numbers in there are close enough already. We're going to do this because when it comes to documentation, this new method that Altium has is going to make our documentation far easier. Okay. The next, I'm going to come back here and I'm going to do the same thing here with the prepregs and the cores. I want 5 mil prepregs on all these layers right here, except for the middle core to be 15. But instead of generic FR4, I'm going to come in here and actually pick a 5 mil dielectric layer right there as this one right here. I'm going to come pick a 5 mil core right here. And I'm going to pick the two 1080s version right there. Now, the next step I'm going to do here on this part of the stack up, you don't have to do this week. It's not required of this week, but we will end up using it in a couple of weeks here when we get to our FPGA. We're going to need to create micro vias for the FPGA escape routing that's in here. So I'm going to go ahead and add a pair of thin layers that I'm going to use for the FPGA. So for that, what I'm going to do is I'm going to select the top layer right here. I'm going to right click on that. And I'm going to say insert layer below, signal.
Hey, Chris, did you mean to put a 15 mil
Yes.
on that
in
last
the
core?
center.
Okay. Okay.
Yes. Yes, I absolutely meant to put a 15 mil there. That was what was there. So now I have this one, and I'm going to pick the thinnest dielectric I can get right here. Okay. I think 2.8 is my thinnest, but I'll double check that. No, 2 mil is my thinnest right here. So I'll pick that one right there. Now, because of the stack symmetry, I only have to do the top half. So I'm changing from an 8-layer board to a 10-layer board. And yes, Edson has a question out there.
Yes. Chris, so when I know is the best choice, we can choose the pre-peg or core. For example, in this case, 8 layers. So you can choose every core or every pre-peg is the same, or what's the best choice? Pre-peg
Hold
or
that
core
thought till
depends.
right. Hold that thought till next week, Edson. It's all about materials. And there are part of it we're going to discuss here in just a moment, which is it's the first off, cores versus prepregs. You always have to alternate. You can't put core. The prepreg are the glue sheets that glue the various different layers together. The cores just have the copper on both sides. So if you have a core here, you must have at least one prepreg sheet here before you have another core from a manufacturing. So next week in materials and the week after in manufacturing, we'll go into that in more detail. From an electrical performance point of view here, though, from a signal integrity, creating our controlled impedance stackups, we're actually going to see that here in just a moment. That's why I have those isola pages. Again, preview of next week with materials, but how we're going to build our stack up here in just a moment. Okay, so there's no one right answer for what is best. With one caveat here, and we talked about this in course 1, and we'll talk about it again in manufacturing. This idea of foil versus cap construction. By far, from a manufacturing point of view, it's always best to have the outermost layer be the prepreg layer, so you've got a sheet of foil. If you make the outermost here a core, it means that outer core has to be going through the etch processing twice, once for the underside and once for the outer side during the plating process. So with few exceptions, we absolutely want to have the foil construction where the outermost layer is prepreg, but then the other is you just alternate a prepreg, then a core, then a prepreg, then a core, and so on. Must be done that way. That's how the manufacturing works. So we're going to get into that when we get into the manufacturing week.
Yes, you must have a pre-peg between cores.
Right. So the core has the 2 coppers attached to it. Then you have a prepreg must be between that. Then another core has 2 coppers. Then a prepreg, then a core, then a prepreg. You can have a prepreg followed by a prepreg, but you can't have a core followed by a core.
Yes, absolutely. Yes, right. Thank you very much.
Okay. All right. So I'm going to do this. Now there's one other thing I'm going to do based off of my own personal knowledge of the material I'm going to show you guys next week is the default materials that are in the Altium pre-made library have 4.3. I know my dielectric constants are going to come in closer to 3.9. So I'm just going to change them here.
Chris, one question. So that is actually what you would find out, let's say, if you get in touch with the manufacturer, right?
Yes, I'm actually going to show you that here in just a second of where I'm getting these numbers.
Okay.
Okay. So I'm going to put these as closer to 3.9. And so let's go back over here and let's assume that I actually wanted to use the isola materials, right? So I said, oops, I pulled the isola up first, meant to do that second. So isola is a laminate supplier, right? This is one of the major suppliers out there of the materials that we use to make the boards, right? The cores and the prepregs that Edson and I were just talking about. Okay. Stupid little banner keeps getting in my way. So I'm going to go over here and I'm going to do an advanced search here, show my filter options, show my slashes. We'll get into all of this material stuff later, but I know I want a 126 material and I'm going to pick the generic 370HR. Many of you have probably already seen this coming from your manufacturers, that they use 370HR as their material of choice if you give them the freedom. This is like a bread and butter material that you will see out there from fabricators. Okay. So I'm going to go down here. Stupid thing. Yeah, whatever. And there's this table here called constructions. Here's all the different cores. And again, we're going to get into this in much more detail next week and the week after when we get into materials and manufacturing. But effectively here, so those cores are, which already are fully cured resin that already have copper bonded to the surface or deposited on the surface. Thought it was very thin two-layer boards. I'm going to look at them based off of what the thickness I want is right here. So maybe like a 5 mil core, that one sheet of 2116. That one I probably could have looked at and left at the 4.1. But for all the others, the thinner layers there, the 5, the 3 and 4 and 5 mil cores, right over here, we can see that I'm in like the 3.5. If I'm at the 2 sheets of 106 construction, I'm in that 3.8, 3.9 range right here. And this is just the test frequency. Am I testing at 100 megahertz, 500 megahertz, 1 gigahertz, 2 gigahertz? The 1 to 2 gigahertz is the range we should be looking at. That's about the test frequency we run all these at. That's the frequency content that's going to be in our digital signals, which we'll see in Signal Integrity Week. So I'm going to say, yeah, 4.0s, 3.9s are pretty typical of this material that we're going to select here. That's for the cores. Then down here in the prepregs, it's even lower. So the individual prepreg sheets, a sheet of 106 right here, that's at like 3.8, 3.83, 3.7, right? And it gets even lower as I go higher and higher in frequency. And we'll talk about this more. So yeah, I'm pulling these numbers off of the data from the manufacturer based off of the specific construction, as opposed to a general average number specified either by IPC or on just the data sheet. So it's not even the data sheet, it's past the data sheet. You have to go to the individual constructions for the layer that we're looking at. So I'm going to use 3.9 as my number here. The bulk of the thicknesses I'm choosing, the 4 and 5 mil layers right there, are going to come in here in that 3.9 type of range right here. Yeah, etc. So that's where I'm getting these from, is right here from the manufacturer. And most of the major manufacturers out there, Isola, Arlon, Nelco, and so on, provide those kind of data. You don't even usually have to call them. It's usually right there on their web page for the sheet. Does that answer your question?
Yeah, it answers my question, but now I have an additional one. So here you showed actually that there is quite a significant list of the, let's say, thicknesses. And in Altium, you have a predefined set of thicknesses from which you can choose from. How does that then work hand in hand?
Okay, so within Altium, in here, if I go up here in the layer stack view, there's actually a materials library. That's just Altium pre-built a library of generic stuff as a starting point. You can actually go in and build your own library if you want, right? So here's prepreg data right here. I clicked on prepreg. Give me their list of prepregs. Come on, Altium. There we go. So here's all the ones that Altium predefined, right? And I don't know if they were using Isola or Nelco or whom they used to reference their materials, but you can always go and that's their cores. I want to go to prepregs, and for whatever reason, it's not letting me in there. Usually it's supposed to have the new button also available so that you can create your own new materials and you can basically build your own library of parts. The other thing you can do is you can pick something off of their list that's close, that's maybe the right construction, right? 2 sheets of 1080, but then you can just come over here to this layer, for example, and I could say, oh, I can just modify it and say, I want this to be Sola, right? And instead of generic FR4, I want to say this is my 370 HR material, right? So you can basically go in and modify the properties over here in your individual Stackup to describe exactly the material you have, as opposed to the generic one. Like I said, Altium comes with a pre-built library, just like with components, right? Altium has a pre-built library of generic resistor, capacitor, and so on. And if you have a new one, you go build a new library part. It's the same thing here with the materials.
Okay, then the following question is, sorry for taking so much time, but
No problem,
the following question is then, if you create this library, can that be shared throughout the organization or throughout
Yeah,
the team?
absolutely.
Or okay,
Absolutely. Yeah. Just like you would
okay,
have any other library, you can have a shared general library of materials. Absolutely.
cool, thanks.
So, okay, so we're going to go over here. I'm going to create this. So now I have created my stack up here. I've gone from an 8-layer to a 10-layer because I've added this extra thin 2-layer out here. I've got signal, then plane, plane, signal, signal, plane, plane, and then my 2 bottommost signals here. Then there's these 2 other tabs down here at the bottom. I'm going to do the easier one first. Again, we're going to get into why this is in future weeks, but for the purpose of building our stack up here, I'm going to demonstrate right now and explain why I'm doing this later. So within the Stackup, the only one you can never delete is the full through via. Every Altium Stackup requires that you allow for the complete full through via from top all the way to bottom. But then I can add any other new vias I want. So I'm going to add a via here. By default, it's always going to be a layer 1 to 2 blind. I'm simply going to change that to be a layer 2 as my start and layer 9 as my bottom. This is what would have been the full through via in the simple 8-layer board. So again, if you come back and take my advanced design concepts class, we'll get into more about the sequential lamination process here. But this is going to be my buried via right here. And then I'm going to add one more via right here, which is one more blind. It's 1 to 2, but I'm going to say it's a micro via this time. And I'm going to say mirror it. So now, nothing in this Stackup is actually defining the size of the via, what the diameter of the pad, the diameter of the hole, or anything like that. This is simply saying the structure. I will allow, in this design, I will allow vias to be defined that exist from layer 1 all the way to layer 10, from layer 1 to 2 as a micro via structure, from layer 2 to layer 9 as a buried via structure, and from layer 10 to layer 9 as another micro via structure. These are the only available allowed via structures or shapes that I'm going to allow. I will go into a rule afterwards and create and define the actual diameters and sizes. Okay, with that, impedance is a little bit longer, but it is our break time. So why don't we take a quick 10-minute break, be back at the 15-minute mark, and then we'll go into the impedance tab down here and see how we're going to add our impedance profiles. And of course, if anybody has any questions, I will of course stay online throughout the break if anybody has any questions. Otherwise, take quick 10 minutes bio break, caffeine break. Be back at the 15-minute mark. Niti, we provided those as part of the class. So if you go over here to our Edge page, back up here. So you should have received an email about IPC DRM credentials, username and password that you'll use. And if you go down here to the bottom of our Edge page, if you have watched the walkthrough, IPC Edge walkthrough video that I posted, right down here, the IPC DRM protected IPC standards. And we have provided as part of this course an entire list of standards that we will use and reference throughout the duration of the course. And you should be able to, if you can't download the entire folder, you should be able to download one at a time. Now note that these are node locked to a single physical computer. So whichever computer you open the first standard on and enter the credentials, all others will then be node locked to that physical computer. But yes, we have provided those for you all here. So there's the 2952, the current, the 2221 that I'm showing you, where the voltage spacing charts are at, 2222, and so on. The 2611, 12, 12-1, 1415, 4101E, the 6011, 6012, right? And so on and so forth. Standard 51, CC 830, SM 840, JSTAN 01. Yeah. 04, 05, and 06 for the J standards, and so on. Yep. And Kelly just posted something out there. Yep. So Kelly also posted to our Edge, to the chat window there. Hey, Kelly, do you mind hanging out after class for about 5 minutes? Yes, Kelly. Yeah, it's a minor thing, by the way, Kelly. This is actually more of a minor thing that shouldn't be an issue on your end, I don't think. But anyways, we'll hang out. We'll talk after class.
Chris, could I ask one question?
Absolutely, that's what I'm here for.
So it is not directly tied to the lectures we're doing right now. It's more tied to the Altium 365. I don't know how much experience you have with it.
A bit.
A bit. Okay, so what we are trying to do, or what we are thinking of doing is going to Altium 365, because up until now we don't have managed libraries, so to say. So we actually are doing all our, let's say, component definition on the schematic level, which is not maintainable. And I was just wondering if you know if let's say, the online libraries, can they be, let's say, managed in a sense that you can limit control of who can do what? Because up
Yes.
until now, what we've had is, that people, when they are in a rush, they just add a component, they don't define anything properly, just that they can use it, and we want to avoid that we have components which are not properly defined.
Yes. So I will say this, there is actually a way to do that as well, even without the Altium 365.
Okay.
There's ways to do that both ways. But yes, with the Altium 365, what you do with those managed libraries, when we're back here under the projects, let me go back here to the main project view. And it's also under components, so there's the managed components here. But just like with the projects, the components have a similar management, and there's a great video on how to do managed libraries in Altium 365. But with any of the files right here, whoever is the administrator of the 365 workspace, those with administrative rights to 365 workspace, can go over here and under the sharing options for that, you can say under the shared, you can say, okay, this particular file here can be shared with workspace members, administrators, and now the owner of the document always has edit rights, right? So whoever creates the library in the 365 workspace should be one of your librarians. So they always have edit rights. And administrators, well, admins, we're the power users. We can do whatever we want, whenever we want. But for all other members, you can give them either no access or view only access or full edit access. And so what you would do is you'd give them view only, meaning they can go get the part, place it in their design, but they can't edit the part.
Okay.
Right. So that's one way. But there is actually completely a way to make libraries that are that are controllable by you, the designers, even without using the Altium 365. And what you do there is inside of Altium itself, one of the project types. So when you go File and you go New and you go New Project right here, if my thing will expand. Come on, Altium, you can do it. Right? Right here, it's a library project. Okay. Into a library project, and yeah, you'd go workspace or file or whatever. All right, so I'm going to cancel out of here because I already have one. All right, so I have, right here, I have what you're basically making is what's called an integrated library, right? So here you can see I have a bunch of integrated libraries, or you can expand those and extract. So right now you're used to building, for example, individual schematic libraries and individual PCB libraries, yes?
Right.
You can take those two libraries and create what's called an integrated library, this intlib, and that intlib can then over here, you know how you've got in your components panel here, you've got all the various different like predefined Altium libraries, which normally you can't go edit. So what I've done in the past at other companies, long before the days of Altium 365 and cloud, is I would just go and have the IT people make me a folder on the server, right, that had restricted access. The librarians had full editing and write capability to that folder, and all other users were read-only to that folder. I'd store all of my libraries in a network location on the folder, and then I'd create these intlibs, and have the int libs as what were actually attached here at the library level here, right? So there's all those int libs. And that way they could go place the part from the components panel over here, and they're never able to edit it. They're only able to place it in their design. They can obviously edit the part, play with the properties and stuff once it's in the schematic, but they cannot mess with the actual library itself. Only the librarian gets to edit that. So yeah, you can do it either as an integrated library package or as a fully online cloud-based managed library.
So so we did use the integrated libraries, but we kind of had just, let's say, an integrated library for devices and an integrated library for connectors. So it was not very, let's say, separated well.
Well, that's just a process thing. I mean, these are ones that I borrowed from a job I did. God, this has got to be about, I don't know, 20 some years ago now, right? I made integrated libraries, so I basically started organizing them by the type of parts. Surface mount digital ICs, through-hole digital ICs, surface mount analog ICs, surface mount through-hole analog ICs, right? And so on. So I basically had it by component type and so on. And so then even down here, I'd get even worse. We had some standard resistor size we used. So I'd have, my 0.1 watt, through holes, or my surface mounts here, right? So, right. So there was my 0603s, my 0402. So I said, okay, you want no 0603 resistor? Here's my 0603 resistor library. So it's just a matter of creating the library. And even then, if you've already created an integrated library for just devices, well, just go start extracting parts out of it. Make a new library. You can re-extract the sources out of the integrated library.
Right.
Yes, so just re-extract your source, schematic lib, PCB lib, start creating a bunch of, schematic libs for digital ICs, analog ICs, resistors, capacitors, so on. Just here's all my caps. Throw them into that one and remove them from the first one, and so on.
Right. I mean, I have to say that the online library that you have on the 365 is quite nice because of the other options like the sourcing and the availability and stuff like that. So it is quite easy to see if something is available or not available.
Well, but you get the same thing even with these, right?
We're
going to actually see that today.
Oh, okay. Okay, cool.
Yeah. So you can actually do that over here once we get, actually, I take that back. That was in my course 1. So let me give you the quick, I think we're already past where we were supposed to be back.
Then we continue other time.
No, it's fine. I'll give you the super quick short version here. So if I have a part in my design, let me go back up here to the existing design. Now let me go over here. Let me put a generic resistor in here, right? If it'll scroll for me. There we go. Oh, I just saw it. Too far. There you go. Resistor, right? Generic 1K ohm resistor. So either at the schematic library level where I'm creating the symbol, or here at the schematic document level, if I go look at the properties of this generic part, right? I have a few things. I have a few PSpice parameters supplied right here, and that's about it for values and parameters, right? And it's just generic resistor. But let's say, for example, I know exactly what part this is I want. And I know it's a CRCW 0805 1K00 FKEA 0805 1K ohm 1% resistor, right? Under this manufacturer's part search, I'm going to go find that. See how it's got the green bar? That says all the parameters are already there. I'm going to right click on that. Right here, and I'm going to say add supplier link and parameters to parts. That's going to ask me which one. I'm going to click on that guy right there. If it's a schematic symbol in the library, schematic library, it'll just automatically add it because you've got only one part open. But here, since I'm in a schematic document, it's there. And now when I go back into my properties, for that part, got to select the part first. Now, not only has it updated all of my descriptions and parameters and things of that nature, but there's all the supplier linking, manufacturer, manufacturer's part number, all that kind of good stuff here. But also, it should have it'll show it in the BOM document there now. But basically, all of, and let me go double click on its properties and pull up the actual properties dialog right here. There we go. So it's got all of the information, it's got the pricing information, and it's live data. So you can actually go do a live data view of the parts of the bill of material. It's what they call their active BOM doc now. But if I was back in the library for it, I would actually see all that information. And you also see it right here on the manufacturer's part search, right? So I've got that view right there, and I can pull the little pull up right here. And so there's all the parameters, model information, alternatives that are offered, you know, and so on. So multiple different parts, tolerances, models, revision controls in Altium, data sheet links, and so on, along with all the live pricing data right here, and so on. So this one is in stock, 6,637. So 6.6 million parts in stock at 0.1, you know, 10 cents each, and so on, whatever.
Right.
So yeah, you by
Okay,
adding
thank you.
supplier
Thank
links
you
and
a lot.
parameters,
Thanks.
you can actually add all of that right to the parts, so that you can get all of that data stored in the design. Okay, back. So hopefully everybody's back from break. Back over here now. So the last thing we're going to do here before we go create some rules is we need to create our impedance profiles. So here's our stack up. We have the add button up here. And every time you click the add button, it's going to default to a single-ended 50 ohm impedance. Okay? So it has created the impedance profile for me for 50 ohms single-ended right here. Now let me pull this over here a little bit. And let me also pull there we go. Let me shrink that size a little bit so we can see this a little bit better over here. Okay. Now, a couple of things though. The tool is making certain assumptions about the structure. For example, this top surface right here, it made the assumption that my reference plane was going to be exactly here on layer 2, which it's not. I'm going to select this one right here, and I'm going to pull the little pull down and say my reference for this is actually plane number 1 right here. Then I'm going to come over here, and I'm going to select this one right here. And we'll see that now my width is increased from 2 mils to say 15 mils. I'm also going to pull this one here and say this one has none for the top reference, hopefully. That has been an ongoing issue for me, is not letting it do the embedded microstrip correctly. But that's okay, because this signal layer here, this is only going to be for escape routing. We're not actually going to allow any digital routing on that layer. We're going to route from here and go directly to our internal layers. But we have the same problem here. On this structure right here, it assumed my reference was here rather than the plane. It did not correctly select that this was a dual strip line structure right here. More on that when we get to signal integrity. So again, I'm going to pull this pull down right here. And I'm going to say the next reference, the bottom reference is going to be this one here called plane 3. Okay. And I should get the same kind of update right here. And we'll see that now we're at 6 mils. So aside from this one, which we aren't actually going to allow any digital routing on this special layer right here, we're going to route out, escape route from there and do all of our digital routing on these 2 layers right here. I don't care that this one is showing underneath. Remember, we just saw that manufacturability thing that says for this 1 ounce copper for etching, my trace width minimum must be 5 mils. So I'm looking and saying, yep, 15 mils there, 6 mils there, I'm fine. I am well within my specified range of allowed widths for manufacturability as well as characteristic impedance. So I've now defined my 50 ohm profile right here. And I do want to make sure that I also have my properties panel open. So we should be able to see those right here, because now we're going to create another profile right here. And for this one, the description here got added just because there was already one. We don't need a description there, but what I'm going to do is I'm going to change this from single-ended to differential. If you're doing RF, we can do the single and differential to the coplanar waveguides outside the scope of this class. So we'll just go to a differential. And we're going to change this to 100 ohms. And again, let it recalculate one more time. And again, it's struggling right here on the outer layer for right now. But the first thing we're going to do is we're going to say again, same thing for this one here. The bottom reference is plane 1. And for this one right here, we're going to change those to be the plane 3. Okay. So now that we're going to do those, now it's recalculated my differentials right here. Now my outer one, that's okay at 5 mils. Again, don't care about the mid layer 2. But this one right here, you'll notice that my width is coming in at 2 point something there, 2.8. We need to be at least at 5 mils. And so for differential, not only do we care about the width of the trace, the thickness of the trace, the height of the trace above the return, but also this gap distance G right here. So we're going to scroll down right here, and we're going to pick this one right here, so it's not on the outer layer. Maybe we're going to scroll down if Altium will wake up. There we go. We're on that layer right there. And what we're going to do is we're going to increase this gap width right here. So instead of having a gap of only 5 mils, that was our minimum, I might make that something like 15 mils. And see where that gets me. And 15 gets me over. So you're basically going to turn the dial on gap width right here and see that, yep, that is going to achieve my 5 mil, my minimum 5 mil gap and my minimum 5 mil width. So I've got my gap and width, my trace and space are both 5 mils or greater. So I'm okay making this out of my 1 ounce copper. Okay. Now that I have completed the design of my Stackup, now what I'm going to do is I'm going to right click on this Stackup right here and say save this Stackup. The Stackup is actually an embedded document interior to the, it's part of the PCB document. So you can only extract it if you have the PCB document open. All right. And once we have the document open, once we have that saved, we can go ahead and close the PCB document itself. I'm sorry, not the PCB, the Stackup document. We'll simply right-click on this and close the Stackup itself. And we now have everything we need defined so we can go create our rules. Okay, once that's closed, we can come back over here to our actual PCB document and we'll go see how we're going to create our rules. Okay, so up here under the design menu, okay, we'll get the rules menu right here. So under design, we'll go to rules right there. See rules. Now, my default, my starting point, I purposely left a couple of unneeded rules in there to demonstrate how to write complex rules. So Altium, unlike any of the other tools on the market, Altium, I feel, has the best or most robust ability to write very complex, very high levels of gradation, right? Of graduation, right? Uh, very detail-oriented rules. So any of these ones here that start with DRV in all capital letters, we can get rid of them, but I just wanted to leave those in there so I could show up front how you could write those. So instead of just having generic rules, make my spacing this, right? If it's in this net class and on this layer and in this other group and so on. So you can do this very specific selection criteria. But for the most part, we're just going to first right click on these ones here that have DRV right here. So there's width rules, clearance rules, and via rules. Again, so there's one that's very complex written and so on. We'll do that first. Now, in each of the major categories, right, electrical, routing, and so on, there's subcategories. Under electrical, there's clearance, short circuit, unrouted, unconnected, modified, and creepage distance right here. Under each one of those, there's usually a generic rule that has the same name as the group. This always gets the scope condition of all, or in the case of clearance, all to all. This is basically the default condition that if the feature you are working with does not meet or fit any of the other criteria that you have in any of the other rules, apply this rule. And this is important because there are cases, engineers have done this in the past, where they think they have rules for everything, but they missed some little feature, right? It's just outside the group enough that the tool didn't know what to do with it, and it got into race or unknown conditions. It hasn't happened in many years, it's over a decade or 2 decades or so. But back in the late 90s, early 20s, early 2000s, right? There would be times where software tools would be like, I don't have a rule for that. I don't know what width to make that line, and so on. So in this case, this is just going to be your absolute bare minimum. I'm going to set this to something small. Now we said our absolute minimum clearance rule was 5 mils. So that's what I'm going to do right here. I'm going to set my absolute minimum to 5, except for copper to holes. This is always going to be 10 mils minimum. This is a manufacturing thing. Again, more on that in manufacturing week. I'm then going to create 2 new rules because I only have 2 specific.
How do you know that it's in mils, and it's not 5 millimeters or something else?
So my rules, okay, that is a great question. Is first, let me add these 2 new rules, and let me go back to my first clearance rule right here. Okay, so, and let me actually go just apply this for now and get back out of here. The reason I know it's in mils and not millimeters, that's a great question, and I should have shown this, but it's really, this is why I wanted everybody to go through that Altium walkthrough tutorial, right, if you've not used it before. When you are out here in the PCB document itself, and you have nothing selected, and you go to the properties panel right here. Oh, and I noticed not all my checkboxes are checked as well. While we're in here, I'm going to do this as well. But down here in my generic properties of the workspace itself, I have control of what my workspace units are. So I work in English, so I set my entire workspace to mils. That means when I'm in the design rules, it's defaulting to mils. If you're working in metric, you would come in here, set this to millimeters, and then everything would be displayed in millimeters. So great question. Was that Alonzo that asked that, I think, or somebody else?
Yes, it was me. Thank you.
Yeah. So yeah, it's basically all of those sub dialog boxes and so on are going to inherit from the document property itself. So I've just set my workspace to be English. I mean, right here.
I have a question, if I may ask.
Sure.
If you're changing from, like, if you set stuff up in mils and then you're switching back and forth, does it lose precision when it tries to, like?
No.
Okay.
Actually, under the hood, Altium works in metric to, I believe it's 12 decimal places. So no, you don't lose any precision when you're going back and forth. And in fact, even though I'm set in mils right here, for example, and I wanted to define my rule in millimeters, for example. So let's go to my new clearance rule right here. And so what I'm going to do is in this one, I'm going to set this clearance rule to be a net class. And this might be my digital net class. And I'm going to go back here and say something like, my personal paradigm or process I use is I name the name of the class, or the name of the rule to the name of the class. So digital clearance, right? So in my net class digital, well, let's say, for example, I wanted digital to be, what was it, like 0.4 millimeters or 0.5 millimeters. I could do that. I could type 0.5 and just type the right here, and it will automatically convert 0.5 millimeters to mils for me because I'm in mils, and vice versa.
Thank you.
Right. Now, one of the other things I do when I'm creating my rules, especially for things like clearance and width and so on, and we're going to see this and understand this more in manufacturing, but one of the things I'm going to do is I'm going to add myself some margin. So if I want my absolute minimum to be 5 mils, I'm going to set my actual clearance to be like 6 mils. That way, if there's any over etching, under etching, etc. from the fabricator, I know that my actual desired 5 mil minimum is actually met. And again, I'm going to come back here and change my copper clearance to 10. And then over here, this one I'm going to do 50 volt. And again, I'm going to change it to the net class of 50 volts. And for this one, now 50 volts and digital could have the same rules. It's just 2 different groupings. But just to show how this works, I'll make this one 1 mil larger, or I'll make this one 7 mils. And again, I'll come back down here and make that one 10. You could also come in here. So if you put a single width up here, it's going to apply to everything. Or you could come down here into the table, like I want via to via, or hole to hole to be larger, but I want track to track can be narrower, and so on. So you can do that. There's also ways to control by layer. So right now, remember we had different clearance rules if it was internal versus external, the B1 versus the A7 columns. I could conceivably go in here and create a more complex rule. We're quickly running out of time today, so remind me next week and I'll be happy to show you the more complex rule creation. But for today, we're going to do this. But the last thing I'm going to show you here is the priorities. So the other thing that Altium does is if a feature belongs to more than one class or group, which is very possible to happen with things like powers and returns, right? Like think if you have a generic net called ground. Ground gets added to digital, to power, to 50-volt analog, etc. So if I have different clearance rules and the same feature exists in multiple different groups, whose rule should take priority? Well, that's why we have a priorities button. The lowest number, or number 1, is the highest priority, number 2 second, and so on. So one of the other things I do is if I'm creating a bunch of rules and I create them out of order, I come in here and you can always increase. Maybe I want digital to have higher priority and I'll move that up. So the digital width or clearance is now going to take higher priority than the analog clearance. So you can increase and decrease priorities to make sure that whichever rule has the largest width or largest trace gap or whatever takes priority. Okay. So I'm going to set those. And I'm going to apply those two for right now. Okay. So that's going to set those. Next, we're going to do width. For the digital width right here, I already have this predefined in there that I have a width. And I'm just going to call this digital. In fact, actually, let me delete that one. Needs a name. Didn't like the fact that I had nothing in the name. There. Now let me delete that rule. And let me create 4 new rules. Okay. Now, first one, the very bottom one here called width, that's just all. Now, one of the things I do for width rules, I always set the minimum of the width rule, except for the controlled impedance rules, to whatever my manufacturing minimum limit is. There's my 5 mils. Then my preferred width is whatever I want it. And then my maximum width, I usually go something large, even larger than this. I might go 1,000 mils, 1 inch wide. The reason being is that when you are routing, if you are using these rules, the width that the trace is allowed to be must be within the range defined between min and max. So for example, if I'm routing a power trace, for example, power distribution, 5-volt trace, for some reason I need to route it some width. And yes, I need to neck down to say a 5 or a 10 mil width to get into the individual pad power pin of a single device. But then when I'm routing it across the board, I might want to make that trace width significantly wider so that it can have a lower inductance, lower thermal, and so on. So I might want to be able to change the width on the fly. So only the little segment that actually connects to the power pin is narrow and everything else is big and fat and wide. Well, if I just have one fixed width, min, preferred, and max, I'm only ever allowed to use that one width. So I set my range from manufacturing minimum to whatever I deem as my maximum. And then I set my preferred to what my rule that I'm going to calculate is. So that's going to be my default case, 5, 10, 1K. Then over here, I'm going to create a rule that is like we said, I've got 1 amp. And for this one, I'm going to go to my net class. 1 amp. And again, I'm going to do the same thing here. I'll do 5 here. Might do 1000 here. And maybe for 1 amp, maybe I'll go a little bit wider just to play with it, and I'll make it 15 as my preferred. Okay. That's what I'm going to do here. Now, you'll see this when you go through the groups. There is actually a 5 amp class in there that I created. This one's going to be my net class 5 amp. And again, 5 here. Now, be careful here. You might get some red text. Your minimum must be less than preferred and max, and preferred must be less than max. So if you ever make one of them out of order, like let's say I'm going to increase this here. So I'm going to go back to that trace with calculator here, and I'm going to say I want 5 amps at 10 degrees C rise, and for internal traces in 1 ounce copper, I need 162, and for external traces in 2 ounce copper, I need 100. So I'm going to go with 165 as my preferred right here. I'm going to go 165 and let that exist on all layers. But you'll notice now this one turned red because it said, wait, you made your preferred larger than max. So I'm going to come back in here to max, make that 1000 again, and now everything is good again. Then I'm going to come over here. I'm going to do one more rule. I've got 10 amp. This one's in my 10 amp class right here. And again, 5 for my absolute minimum, 1000 for my absolute maximum. Come back here to my trace width calculator again. 10 amps, 10 degrees C rise. 1 ounce internal, 600 mils. 2 ounce external, 333. 1 ounce internal, 555. So I'm going to go with 560 and give myself some margin. Like that, 560 mils width for internal. Okay. Then finally, I'm going to go with my digital. Now for this one, I'm going to go to my digital net class, but now instead of actually typing with rules in, I'm going to just say use impedance profile and say use my 50 ohm impedance profile that we created in the Stackup. And you'll notice it auto-populated all of the information on all the different layers for me. Okay. In fact, even here on that 10 mil, we could go here and say, well, we needed 560 on the outer layers, but on the inner layers, we could say we were 350. Right? So I can also do it that way and say, depending on what layer I'm on, I can apply those. I'll apply that set of rules. Then I'm going to go to my routing vias. This is
I have a quick question for the digital. So we talked about the manufacturability with the 5 mil being your minimum. This has some traces that are smaller than 5 mil. Is that an issue?
We were just talking about that when I was creating that. I'm going to prevent my digital from routing on that layer, and we'll see that.
Oh, okay.
But the one thing I didn't do yet was my priorities here. Again, I always want the highest width to take priority. So what I'm going to do is I'm going to move my 10 amp up, my 5 amp up, and my 1 amp up, or I could just move my digital down so that they're in that order. So there's my preferred widths: 350, 165, 15, and then 50 ohm impedance profile for digital. So that's the priority list I want. I'm going to close that, and I'm going to apply. All right. Now I've got this one here called routing layers. By default, the all condition is I allow something on all layers. But I'm again going to create a new rule right here. And I'm going to say digital routing layers. and I'm going to say net class digital, and I'm going to prevent those two signal layers that had where it said it was trying to do like 1.6 mils. So I'm using that just to make my escape via for the micro via to get down to the next layer, and then from there I'll attach to a stacked via, which is then going to let me go down to my buried via, which will let me go down to my inner layers, these layers mid 1 and mid 2 right here. So now by doing that structure right there, I've now effectively said, if it's in the digital class, I'm not allowed to have any trace routes on those two layers because of that manufacturability problem. Without spending the time to go back and create an impedance profile there, this is what we're going to do right here. Okay. So that's going to take care of that. Next, we're going to do the routing vias. In the same way, again, I'm going to make the assumption here for those people coming back from PCB1, we went through how to size the play through holes. For those new in PCB2, what we're going to say is that we're going to want a 10:1 aspect ratio as our minimum aspect ratio with a 10 mil minimum mechanical drill size and 20 mils over the hole size to be our pad size, and so on. So I'm going to simply go into my routing rule here. However, there's a caveat here. I'm also going to define my micro via size right here. So my absolute minimum is going to have a via diameter of 10 and a via hole of 5. That's only going to be my micro via. My maximum I'm going to do is say a 50 mil diameter with a 30 mil hole. And then my preferred size is going to be a 35 pad with a 15 mil hole. Follow these three numbers. We'll talk about that more in manufacturing of why I chose these sizes. Okay. So that just sets my min and max must be between 10 and 50 and 5 and 30 for the pads and the holes. And my preferred is a 35 pad with a 15 mil hole. Whatever hole size, add 20 for mils, and that'll be the pad size for level A producibility. Okay. Then the last thing we need to do in here, well, two last things, is our differential pairs routing. Okay. Again, I'm going to create a new rule. And I'm going to say diff pairs routing. And I'm going to say diff pair class, diff pairs. And again, I'm just going to tell it to use the impedance profile we calculated right here. And I'm going to say that one. You know what? I'm going to go back up here to that routing layers. And I'm going to add one more new rule because the diff pairs have the same problem. Because not all the diff pairs are digital. Some of the diff pairs are analog, as in the inputs of the pressure transducer and the thermistor. So I'm going to go to this one. And I'm going to do diff pairs routing. And again, a diff pair class, diff pairs. And I'm going to have the same restriction here. Those two layers that we're trying to be too thin. So I've done all that. The last thing I'm going to do down here is in the planes area right here. For these, I can modify the generic ones here. For the plane connect under all, I'm simply going to go to the advanced and say for vias, I want direct connect. All of this I can leave as default. Plane clearance is fine at 20 mils. That's good for our manufacturing. And for polygon connect, which is our copper pores that might be on our surface layers. Again, I'm going to go to my advanced tab right here. The other thing I'm going to do is 45-degree angles instead of 90-degree angles for those two. And again, vias, instead of relief connect, I'm going to do direct connect. I'm going to apply, and I now have 100% of my rules created. Looks like we are just about out of time today. So let's worry about this week. Let's get all of the rules and stackups created like I did here. And next week, we'll actually start worrying about routing and so on. All right. Any last questions on how I just created and defined these various rules in here?
Can you show the plane connect properties one time?
Yeah. sorry, let me go back into that because I hit the apply and or I hit the OK button, which applies them and closes it. So let me go back in there. So on plane connect is exactly the same as polygon connect, except planes only ever have the played through holes. There's never a surface mount pad on a plane. So I hit the plane connect, condition all. I just said advanced, and I just said the only reason I'm doing the advanced is because I always want my vias to be a direct connect to whatever copper they're connected to. There's no reason to put the thermal ties on a via because we're not ever intending to solder to a via. So there's no reason to do that thermal impedance to allow soldering to a feature that's never supposed to be soldered. So in that way, I'm doing, all I want to do is vias change to direct connect, pads maintain the relief connect with the 4 spokes, and leave the sizing and the gaps here the defaults for now.
Thank you.
Yep. All right. Great questions. Any other questions before I close this out? Okay, if that's that, I will see everybody bright and early, next Monday morning. And next week, we'll actually spend more time doing the routing and the pre-routing of rooms. We'll see how to use the copy room formats, and then we'll get into placing parts into the design. All right. And with that, everybody have a great rest of your
Thank you very much. Thanks. Bye-bye.
Thank you. Have a good weekend.
Okay.
Right.
Bye, guys.
Take care.
Okay, and I'm gonna go ahead, pause.